Imagine an empty concrete room.
Okay.
It's totally brutalist,
Okay.
stark walls, no windows, and right in the dead center sits a pristine matte black server rack.
Just humming away.
Well, no, that's the thing. It's completely powered down. It's heavy, it's silent. But as you stand there and watch, thick black smoke just starts pouring out of its ventilation grills.
Oh.
Yeah. The smoke descends, it starts pooling on the concrete floor, and it just fills the whole space with this dense, toxic fog.
That's a really striking image because it captures a physical reality that we usually, we just abstracted away.
Right, because it's the cloud.
Exactly. We treat digital infrastructure as if it's weightless. We talk about the cloud as if it's just, math hovering in the ether somewhere. But that smoke represents something incredibly tangible.
It represents cash, literally
Cash.
burning cash.
Yeah.
That smoke is the physical manifestation of $27.1 billion.
Just a staggering number.
It really is. That is the projected amount of capital that enterprises are going to burn on completely idle, unused cloud computing assets by 2026.
Just sitting there doing nothing.
Doing absolutely nothing. We are looking at a multi-billion-dollar bonfire.
Yeah.
So, welcome to today's deep dive. If you are listening to this, you are probably someone who wants to understand the hidden mechanics of the tech world, without drowning in an ocean of acronyms and jargon.
Right. We want to actually decode how this stuff works.
Exactly. Our mission today is to unpack this massive cloud waste crisis. We're going to get into why brilliant, highly paid engineering teams consistently and predictably over-provision their environments.
Which they do a lot.
All the time. We're going to explore why the traditional methods, like those scheduled quarterly audits used to clean up this mess, are structurally doomed to fail.
They're just totally broken by design.
Yeah. And finally, we'll look at how the industry is making this massive shift toward continuous application-aware autonomy to actually solve the problem.
It's a huge paradigm shift.
It really is.
Yeah.
And we've got a great stack of sources today. We're pulling from the 2025-2026 cloud wastage statistics. We have some really dense engineering breakdowns from SADAI, Kubernetes optimization research from Cast AI, and this fascinating philosophical framework on something called restorative engineering.
Which is such a cool concept.
It really is. But before we get to the philosophy, we have to talk about the scale. Because the scale of this leakage is just, it's mind-boggling.
The scale is what first catches your attention when you look at the raw data. When you look at the projections, global cloud spending is on track to hit $723.4 billion by 2025.
Wait, billion with a B?
Billion with a B, nearing $1 trillion. And out of that staggering figure, the baseline cloud waste across enterprises, it just sits stubbornly between 28% and 35%.
That's insane. You are looking at nearly a third of all cloud capital, just essentially evaporating into the atmosphere.
Nearly a third of a $750 billion market. And it's not just a general leakage. If we zoom in on specific architectures, take Kubernetes, for example, which has really cemented itself as the default orchestration layer for, containerized applications.
Right. Everyone uses Kubernetes now.
Basically everyone. The inefficiency there is even more pronounced. In those specific environments, enterprises routinely overestimate their resource needs by up to 40%.
40%?
Up to 40%. That means somewhere between 35 and 45% of the underlying virtual machines powering those clusters are running at sizes vastly larger than the workloads actually require.
Okay, so let's drill into the why here.
Yeah.
Because it is so easy to look at a 40% over-provisioning rate and assume, gross negligence.
Right, like the engineers just don't care.
Yeah, they're just lazy. But engineers don't spin up massive, unnecessary clusters just to sit back and watch the AWS bill climb for fun.
No, nobody wants to waste money on purpose.
Exactly. So there is this fascinating concept in the operational blueprints we're looking at today called restorative engineering. And it reframes this entire dynamic around something deeply human. It reframes it around the psychology of fear.
Yes. The fear aspect is so critical to understand.
There's a specific historical anecdote from the source material that illustrates this perfectly. Do you want to walk through that?
Oh, the factory worker observation. Yes, this is a great story. So a team of systems engineers was studying a manufacturing facility. And in this facility, workers had to physically handle explosives on the assembly line.
Like actual C4 or something.
Exactly, real explosives. And the engineers noticed that the baseline state of these workers was just sheer terror. Every single movement was hyper-calculated.
I mean, actually.
Right. They moved like people holding their breath, constantly bracing for a catastrophic failure. Because if they dropped something, it wasn't a bug report. It was a physical disaster.
So the engineers come in, and they design a robotic process to handle the actual transfer of the explosive materials. They absorb the physical risk into the automation.
Right. And the critical insight there wasn't just about, operational efficiency or saving the company money on liability insurance.
No, the defining metric of success, the thing the engineers were proudest of, was that at the end of the shift, the factory worker could pull out their phone and text their family, "I reached home safe tonight."
Yeah. The core philosophy of restorative engineering is that technology, when it's applied correctly, it removes baseline fear. It restores human dignity.
It gives people their peace of mind back.
Exactly. Now, obviously, handling high explosives in a factory is very different from configuring a deployment manifest in an air-conditioned office.
Nobody is going to physically explode if a server crashes.
Right, thankfully. But the underlying psychological driver, that fear of catastrophic failure, is identical.
Because a DevOps engineer, they're never going to get fired because their monthly cloud compute bill was 15% higher than the finance team forecasted.
Never. Finance will complain, but no one loses their job over a buffer.
Right. But if that exact same engineer provisions a cluster too tightly and there's a sudden spike in traffic, and that causes CPU throttling, cascading latency, and ultimately brings down the core application on Black Friday.
Oh, that is a career-ending event.
You are clearing out your desk on Monday.
Yeah, exactly. The incentive structures in corporate engineering are entirely asymmetrical. The engineer's primary directive is reliability.
Keep the site up at all costs.
Yes. Their secondary directive is performance. Make it fast. Cost efficiency. That is a distant third if it even registers at all during the architecture phase.
So they build a safety buffer.
A massive one. They look at the peak historical traffic, they double it just to be safe, and they provision for that absolute worst-case scenario.
It's like, if you think about it like packing for a trip, it's like packing a 100-pound suitcase for a 2-day weekend trip. Just because you are terrified you might suddenly need, I don't know, a winter coat, a tuxedo, and scuba gear.
Just in case.
Just in case. You're completely safe. You have every single contingency covered. But the baggage fees are going to bankrupt the trip.
That's a perfect analogy. And in the corporate environment, the person packing the suitcase isn't the one paying the baggage fees.
Oh, that's such a good point.
You have the engineering team optimizing for survival, and then entirely siloed from them, you have the FinOps or finance team looking at trailing averages and just screaming about the budget.
They're speaking two entirely different languages.
Totally. Engineering provisions for the absolute peak, while finance audits for the median. And in the massive gap between those two viewpoints, that $27 billion quietly catches fire.
It just goes up in smoke. So let's open up that 100-pound suitcase and look at what is actually driving the weight. Because the waste isn't just a monolithic block of unused servers, right?
No, it categorizes into distinct failure modes. The sources break this down into what we can call the 4 horsemen of cloud waste, and they all compound at different rates.
All right, so let's go through them. The largest chunk, which the report says about 10 to 15% of an average enterprise invoice, is simply idle compute.
Yeah, this is the most common one. This is your standard EC2 instance on AWS or a virtual machine on Google Cloud that was spun up for a specific workload but never decommissioned when the task ended.
Just forgotten about.
Exactly. But it goes deeper than just forgotten workloads. A massive driver of idle compute is non-production environments.
Oh, like staging and testing.
Staging, testing, development clusters. Roughly 44% of all cloud spend is allocated to non-production.
Almost half. That's wild. And development environments are typically only actively used during business hours, right?
Exactly. If a developer works a standard 40-hour week, there are 128 hours left in that week. All the nights, all the weekends, where that staging environment sits completely untouched.
But the meter is still running.
The meter runs 204/7. Yet, because of the friction involved in tearing down and rebuilding infrastructure, teams just leave them running. They treat cloud infrastructure like a physical data center.
Right, because in a physical data center, you wouldn't unplug a server on Friday at 5 p.m. and plug it back in on Monday morning. That would be insane.
It would be ridiculous. But in the cloud, leaving it plugged in means you are paying by the second for a machine doing zero computational work.
And I think that friction is really real for engineers. Even with infrastructure as code tools, like Terraform or Pulumi, there is always this baseline anxiety that if you tear down the staging database on Friday, it might not spin back up with the exact same state or seed data on Monday morning.
Exactly. It was working on Friday. I'm not touching it.
Yeah, so the easier path is to just let the meter run. Who cares? It's the company's money.
Which leads us to the next layer of the debris field. When instances actually are finally terminated, the cleanup is very often incomplete.
Okay, so this is category 2.
Yes, this is what we call orphan storage. It accounts for another 3 to 6% of the waste, and it is insidious because it generates zero operational noise.
It's a silent killer.
Completely silent. So, in a cloud environment, compute and storage are decoupled. You have your compute instance, like the brain, and attached to it over the network is an elastic block store volume, the hard drive.
Right.
When an engineer decides to kill the compute instance, the default behavior of many cloud provider APIs is to terminate the instance, but detach and preserve the storage volume.
Wait, it just leaves the hard drive floating there.
Just floating in the void. The logic makes sense from a data preservation standpoint. The cloud provider assumes, hey, maybe you want to attach that data to a different machine later. They don't want to delete your data.
Sure, that makes sense.
But operationally, engineers terminate the instance, they verify the application is down, and they move on to the next Jira ticket. They completely forget that the 500 gigabyte storage volume is still sitting there.
Oh, man.
And depending on the tier of that storage, especially if it was provisioned with guaranteed high IOPS, input-output operations per second, you are paying a massive premium for a high-performance drive that is connected to absolutely nothing.
It's like renting a super expensive climate-controlled storage unit and putting absolutely nothing inside it.
Exactly. And then you have the governance failures compounding the storage issue.
Right. The source has mentioned infinite compliance snapshots. This one blew my mind.
Oh, that is a classic trap. So an enterprise sets a strict disaster recovery policy. They mandate a backup snapshot of the primary database every 24 hours.
Makes sense. Good practice.
Good practice. They configure the automated job, they verify the backups are working, they check the compliance box for the auditors, and they feel great. But they fail to set an aggressive lifecycle expiration policy. So fast forward 3 years, the company is now paying to store over 1,000 snapshots of a database state from 2023 for an application that might have been deprecated 6 months ago.
It is purely digital hoarding at hyperscale.
Yeah.
They're just piling up trash.
Yes, and they pay for every gigabyte of it.
Okay, so we have idle compute and orphan storage. I want to look at the third category because this one feels like the absolute most difficult to detect operationally.
Yes.
Zombie jobs.
Yes. These are brutal.
We are talking about data pipelines, MapReduce clusters, or Kubernetes namespaces that are actively consuming resources but producing zero business value.
They are the hardest to catch because if you look at them through a traditional infrastructure monitoring dashboard like Datadog or something, they look perfectly healthy.
Right, because they're often running at high CPU utilization.
Exactly. Say you have an Apache Spark cluster running on EMR, and it gets stuck in an infinite retry loop because it encountered a malformed data row it doesn't know how to parse.
It just keeps trying and failing.
Yes. The CPU on the worker nodes is going to be pegged at 90%.
So the hardware thinks everything is great. Look how hard I'm working.
Right. The processor is churning, garbage collection in the memory heap is firing constantly, the network is passing data back and forth between the driver and the executors.
Yeah.
From an infrastructure perspective, that is a highly utilized active cluster.
But from a business logic perspective, it is a total zombie.
A total zombie. It is burning thousands of dollars an hour, and the output queue is completely empty. It's doing nothing useful.
Or take a Kubernetes namespace. The reports highlighted this. A development team embraces GitOps, right? They open a pull request for a new feature.
A very modern workflow.
Yeah. The CI/CD pipeline automatically spins up a dedicated Kubernetes namespace with its own pods, services, and ingress controllers just to test that one specific code branch.
Which is brilliant for developer velocity. You get a perfect sandbox to test in.
It's awesome. But then the developer merges the code, the feature goes to production, they celebrate, and the webhook designed to tear down that temporary namespace fails silently.
And no one notices.
No one notices.
Yeah.
The cluster autoscaler sees that there are pods requesting CPU and memory in that namespace, so it keeps the underlying EC2 nodes spun up to support them.
Forever.
Forever. No user traffic is ever going to hit that namespace again. It is a ghost town, but it demands electricity and capital to maintain its existence.
And that brings us to the final category, which isn't really an engineering failure at all. It's a purely financial engineering problem. Oversized reservations.
Ah, the timing problem.
Yes. So, cloud providers incentivize you to lock in. If you commit to a certain level of compute usage for, say, 1 or 3 years through a savings plan or reserved instances, they will give you a steep discount.
Sometimes up to 50% off the on-demand rate.
Exactly. It's a huge discount. So the enterprise finance team looks at their monolithic application, they calculate the baseline load, and they buy a massive 3-year compute commitment to secure that discount.
Which makes perfect sense on a spreadsheet.
It looks brilliant to the CFO. But 12 months into that 3-year contract, the engineering team executes a major modernization initiative.
They read a blog post and decide to rewrite everything.
Pretty much. They refactor the monolith into microservices running on a serverless architecture, like AWS Lambda or Fargate, where you only pay for the exact milliseconds the code is executing.
So the engineering team celebrates because they've modernized the stack, they've improved scalability, they're deploying faster.
But the finance team is weeping.
Right, because they realize they are still legally obligated to pay for the massive legacy compute capacity they reserve for the next 2 years.
The architectural evolution outpaced the financial commitment. So the utilization rate of their discount plummets, their new serverless on-demand costs spike, and they effectively end up paying double for the same workload. The commitment outlives the architecture.
It's a mess. Okay, so looking at this ecosystem of waste, we have the idle non-prod environments, the orphan storage, the zombie loops, the stranded reservations. It raises a really fundamental question for me about the relationship between the enterprise and the cloud provider.
Okay, what's that?
If I have a massive storage volume that has had 0 read or write operations for 90 days, or an instance with 0 inbound network connections for a month, why doesn't AWS or Google Cloud or Azure proactively shut it down?
Why don't they just help you out?
Yeah. Why is the entire burden of detection and remediation placed on the buyer? It seems crazy.
Well, it comes down to liability. And the foundational business model of public cloud infrastructure, the hyperscalers operate on what is known as the shared responsibility model.
The shared responsibility model.
Yes. Yeah. They guarantee the security and availability of the cloud, meaning the physical data centers, the hypervisors, the core networking backbone. They make sure the lights stay on.
Right.
But you, the customer, are responsible for what happens in the cloud. Your data, your applications, your configuration, and critically, your efficiency.
So they provide the raw materials.
Yeah.
If you want to use those materials to beat a machine that does nothing but spin its wheels and burn fuel, that is your prerogative. They're just selling the gas.
Precisely. They will happily provide you with a dashboard of recommendations, things like AWS Compute Optimizer or Google Cloud Recommender.
Those little yellow warning icons.
Right, advising you that a resource looks idle, but they will never autonomously cross the boundary to terminate your infrastructure for you.
Because what if they're wrong?
Exactly. The liability of a cloud provider making a bad assumption and accidentally tearing down a critical dormant system, say, a failover node for a hospital's database, is infinite. They sell the capacity. How efficiently you pack it is entirely your problem.
So the enterprise has to build its own immune system to fight this waste.
They're on their own.
And historically, as the sources point out, the primary weapon has been the FinOps team running a manual scheduled audit. They pull the billing data at the end of the month or maybe the end of the week, put it in a massive spreadsheet and try to hunt down the inefficiencies.
The dreaded spreadsheet.
Yes. And examining the operational data we have here, it becomes immediately clear why this batch process approach is structurally doomed.
It is structurally guaranteed to fail. You cannot fix a continuous billing problem with a batch process human review. It is a fundamental mismatch in frequency.
Let's trace the timeline of how a manual audit actually fails in practice. I love this example from the sources.
Yes, the GPU example. Let's walk through it.
Imagine an engineer spins up a massive GPU-accelerated instance on a Tuesday morning to train a machine learning model. These things are really expensive, right?
Very expensive. We're talking dollars per hour, easily.
Right. So by Tuesday afternoon, the model converges, the job finishes, and the instance goes idle. The engineer meant to turn it off, but they got pulled into a high-priority meeting and just forgot.
Happens every day.
Wednesday passes. Thursday morning, they jump back on, run a quick inference test for an hour, and it goes idle again. Finally, Friday afternoon rolls around, and the FinOps team runs their weekly resource audit.
Okay, so when FinOps runs that scan on Friday, what do they actually see? If the scan happens to query the API during the one single hour on Thursday when the instance was active, the instance might not even get flagged as idle.
The scan thinks it's a vital piece of infrastructure.
Exactly. Or, let's say it does get flagged. The FinOps analyst looks at the tag, sees it belongs to the data science team, and sends an email asking, hey, can we terminate this instance?
And it's Friday afternoon.
It's Friday afternoon. The data scientist leaves for the weekend. They see the email on Monday morning, investigate to make sure they have their weight saved, and finally reply on Tuesday, yes, you can kill it.
So the instance is terminated on Tuesday. But look at the billing reality here. The meter in the public cloud runs by the second.
Yep.
From Tuesday afternoon to Thursday morning, and from Thursday afternoon all the way through the entire weekend until the following Tuesday, that massively expensive GPU instance was racking up charges.
Non-stop.
The audit eventually caught it, sure, but the delay between the event and the remediation cost the company thousands of dollars.
The audit didn't prevent the waste, it merely documented it. The batch process guarantees massive billing gaps. It's unavoidable.
And even when teams try to speed this up using the cloud provider's native recommendation tools like AWS Compute Optimizer, the human bottleneck still remains.
Oh, absolutely. The native tools are essentially just sophisticated coping mechanisms for the absence of a closed control loop.
What do you mean by that?
Let's say you use a recommendation engine, and on Monday morning, it generates a list of 200 highly probable waste items.
A nice, neat list.
Right. But a human operations engineer still has to evaluate that list. They start at item number 1. They have to pull up Datadog or Prometheus to verify the metrics. They have to cross-reference the resource tags to figure out who the business owner is.
Which is probably wrong anyway.
Usually wrong. Then they have to ping the owner in Slack. They have to wait for approval. They have to schedule the termination during a maintenance window so it doesn't trigger a false alarm in PagerDuty.
The operational overhead of just investigating the waste is staggering. It takes hours.
It takes days. By the time that engineer fights through the friction to get to, say, item number 50 on the list, 2 weeks have evaporated.
Wow.
And during those 2 weeks, the application architecture has naturally shifted. Deployments have happened. Traffic patterns have changed.
Right, code is constantly shipping.
So items 51 through 200 on that original list are now completely stale data. They're useless. The environment is moving at machine speed, and the cleanup crew is moving at human speed.
It's like we are trying to bail out a sinking ship with a sieve. The very structure of a time-based human audit guarantees that the water keeps rising.
You'll never catch up.
So the logical conclusion is that we have to move to real-time continuous detection. We need a system that watches the infrastructure constantly.
Which sounds great in theory.
But the moment you start talking about continuous detection and automated action, you run headfirst into a massive technical danger. False positives.
Yes. This is what terrifies SREs.
Right. If the system relies on the wrong signal to determine if a server is dead or alive, it will cause catastrophic damage. It'll start tearing down production.
And for a very long time, the industry relied on a deeply flawed heuristic, CPU utilization.
Which seems incredibly logical on the surface.
It does. You write a script that queries the hypervisor, and if the central processing unit of a virtual machine has been hovering below, 3 or 4% utilization for 72 hours, the script flags it as idle and recommends termination.
It makes sense. If the brain of the computer isn't thinking, the computer isn't working. Kill it.
It makes perfect sense right up until that script terminates a critical asynchronous process.
Okay, give me an example. Let's look at the banking example from the research.
Consider a global financial institution running transaction reconciliations. Throughout the day, thousands of edge servers are collecting microtransactions and dumping them into a massive queue.
So the data is just piling up.
Right. And then at 2 a.m., a centralized batch processing cluster wakes up to pull from that queue, run a massive reconciliation algorithm, and update the master ledger.
So for 23 hours of the day, that central cluster is doing absolutely nothing.
Nothing. The CPU is sitting at 1%.
It looks entirely dormant.
But at 2 a.m., it spikes to 95% CPU utilization for exactly 1 hour while it crunches the data. Now, if your continuous detection script runs an average over 24 hours, the aggregate CPU utilization is negligible. It's like 4%.
So the script flags the instance as waste.
Exactly. And if an automated system or an overly zealous FinOps analyst terminates that instance at 4:00 p.m. because it looks dead, they just destroyed the bank's entire daily ledger process.
Judging the value of a system solely by its CPU is like walking past a high-end sushi restaurant at 3 in the afternoon.
Right.
You look in the window, the kitchen is spotless, the chefs are just standing there prepping, there are 0 customers, and it is completely silent. If you judge the business by the noise level in that exact moment, you assume the business is dead and you break the lease.
You'd think they were bankrupt.
But if you look at the actual output, the revenue generated during the dinner rush, it's the most valuable square footage on the block. You cannot judge utility by noise, you have to look at behavior.
Which is exactly why the paradigm is shifting aggressively toward application-aware signals.
Application-aware also.
Yes. We have realized that infrastructure, hardware metrics, CPU, memory pressure, they're often lying to us. We have to stop looking at the hardware in a vacuum and start looking at what the software running on top of it is actually experiencing.
So how do we do that?
The industry is adopting the 4 golden signals. These were established by Google's Site Reliability Engineering Framework.
The famous Google SRE book, Latency, Errors, Traffic, and Saturation.
That's right, LETS. So if we are trying to replace a flawed CPU script with a sophisticated application-aware detection model, how exactly do we apply these signals? Let's walk through the mechanics of how engineers actually distinguish active infrastructure from a zombie using this checklist.
Okay, let's start with a standard EC2 instance or virtual machine. If we aren't using CPU as the primary metric, what is the definitive signal?
You look at network input-output coupled with active connections. A machine can have low CPU because it's simply waiting for a downstream database to respond.
It's just sitting there waiting.
Right, but if an instance has negligible CPU, 0 bytes of inbound network traffic over a sustained rolling window, say 14 days, A&D, 0 active TCP connections established with any other node in the virtual private cloud, it is a ghost.
Nobody is talking to it, and it is talking to no one.
Exactly. It is entirely disconnected from the nervous system of the application.
Okay, what about serverless environments? Functions like AWS Lambda, these are designed to scale to 0. Being idle is their natural state. You can't flag a Lambda function as waste just because it hasn't run today.
No, with serverless, you have to look at invocation frequency over a much longer time horizon paired with error rates.
How does that work?
The signal for a dead Lambda function is 0 invocations over a rolling 30-day window. But, and this is crucial, you must verify the error rate is also 0.
Why does the error rate matter if it's not being invoked?
If invocations are 0 but the error rate is spiking, the function isn't dead, the trigger mechanism upstream is broken, and the function is failing to execute.
Oh, so it's trying to run but crashing.
Exactly. But if both invocations and errors are 0 for a whole month, the function is just orphan code sitting in the registry costing you money.
That makes perfect sense. Now let's tackle the batch processing problem. The EMR cluster, stuck in a retry loop that we talked about earlier. We established that the CPU is pegged at 90%, so hardware metrics say it's highly valuable. The network is active. How do you detect a zombie when the traditional signals are screaming that it's alive?
You have to establish a statistical baseline for the application's temporal behavior.
Temporal behavior, meaning time.
Yes. You look at the historical execution time of that specific job. Let's say you calculate the 90th percentile, the P90, of the job's duration over the last 3 months.
Correct.
If 90% of the time this job successfully finishes in 4 hours, you set an algorithmic threshold. If the current job execution time exceeds twice the historical P90. So if it has been churning for more than 8 hours, the system flags it.
The application behavior, the duration, overrides the hardware metric of the CPU.
Exactly. The cluster is technically active, it's doing math, but functionally, it is dead. It's stuck.
Okay, and for streaming analytics, like data flow pipelines.
Very similar logic. A streaming pipeline might have 20 worker nodes provisioned. You don't look at the CPU of the workers. You look at the business metric, output rows per second.
The actual work being produced.
Right. If worker nodes are greater than 0, meaning they are spun up, but the output rows per second drops to 0 for a sustained period, say 30 minutes, the pipeline is jammed. The workers are active, but no value is being produced.
Finally, let's look at the Kubernetes namespace scenario we discussed earlier. The CI/CD pipeline built it, but the teardown webhook failed.
This is a great one because this is where application-aware signals have to bridge the gap between operations and development tools.
It has to look outside the cluster.
Yes. You monitor the ingress controller for that specific namespace. If there are 0 inbound HTTP requests per second for 7 days, that is a strong signal. But to be absolutely safe, the continuous detection system integrates directly with the version control API like GitHub or GitLab.
Oh, that's smart.
It cross-references the idle namespace against the pull request. If the namespace has zero traffic, ND, the GitHub API, confirms that the specific developer branch associated with that namespace has been merged and closed. You have 100% certainty.
The feature shipped. The namespace has outlived its purpose. Kill it.
Exactly.
Okay, so we have defined the ecosystem of waste. We know why human audits fail. We have this specific application-aware signals required to safely identify dead weight without relying on flawed CPU metrics.
The blueprint is there.
But having the architectural blueprint is vastly different from actually building the building, right? How does an enterprise physically transition its tech stack, and more importantly, its engineering culture, away from manual spreadsheets to a fully autonomous, self-healing infrastructure?
It does not happen overnight. The frameworks in the source material suggest a highly structured three-step evolution. It is a progression of trust as much as it is a progression of technology.
Let's analyze step one, the baseline. The sources call this the reactive manual phase, and I assume this is where the vast majority of Fortune 500 companies are currently stuck.
Oh, without a doubt. Step one is characterized by high operational friction and massive leakage. This is the world of the FinOps quarterly audit. Companies try to solve the problem with governance instead of engineering.
Meaning they just make rules.
Exactly. They implement strict tagging mandates, forcing developers to add metadata tags like cost center or owner or project to every single cloud resource they provision.
So they buy those traditional dashboarding tools to visualize the billing data.
Right. But the tags break.
Constantly. I mean, developers misspell tags all the time.
Or they use a Terraform module that accidentally strips them out. Or, and this is the most common one, the engineer who owned the resource leaves the company and the tag points to his deactivated email address.
So FinOps teams spend half their month just chasing down untagged resources. Who owns Cost Center 404?
Yes. It is entirely reactive. The waste has already occurred. You are literally just arguing over whose budget pays for it. This is the stage where that 35% waste figure is just a permanent reality.
It's just accepted as the cost of doing business. So a director of platform engineering realizes the spreadsheets are failing, the tagging strategy is a nightmare, and they push the organization to step two, continuous detection and visibility. How does the technical architecture actually shift here?
Moving to step two means decoupling cost visibility from delayed billing reports and tying it directly to real-time operational telemetry.
So moving away from the monthly invoice.
Right. Instead of waiting for the cloud provider's cost and usage report, which can be delayed by 24 to 48 hours anyway, the enterprise deploys continuous monitoring systems. These systems utilize read-only API access to scan the environment constantly.
And they're looking at those four golden signals we just discussed.
Exactly. They connect to Datadog, Prometheus, or the native CloudWatch metrics. They pull the real-time latency, traffic, and error rates of the applications, and they mathematically map those operational signals back to the underlying infrastructure costs.
So they build a real-time graph of where the money is flowing and what it is actually achieving.
Yes, and the immediate impact of just turning the lights on is staggering. The data indicates that by simply achieving this continuous application-aware visibility, teams can identify 15% of reclaimable spend within 48 hours.
Wait, 15% in 2 days?
In 2 days, and they haven't changed a single line of code. They haven't terminated a single instance. Just by looking at the right signals, a massive layer of the waste becomes immediately obvious.
It's just hiding in the dark.
Exactly. But visibility is only a prerequisite for action. Step two is still incomplete. You have a perfectly accurate real-time list of what needs to be downsized or terminated, but a human engineer still has to log into the console and execute the change.
The human bottleneck is still there.
It remains. Which brings us to the ultimate destination, step three, fully autonomous execution.
This is the Rubicon. This is where you connect the continuous detection loop directly to an execution engine. You give the software write access to the production infrastructure.
Yes. You remove the human from the optimization loop entirely. The algorithm monitors the application behavior in real time. If it detects that a microservice is over-provisioned, perhaps the latency is incredibly low and the saturation is minimal, the system autonomously issues an API call to the orchestrator to scale down the replica count.
Or it shifts the workload to a cheaper instance family.
Right. And if it detects a zombie data pipeline matching the statistical parameters we discussed, it terminates the process without waiting for a JIRA ticket to be approved.
It just kills it. Now, before we talk about the safety mechanisms that make this possible, because I know engineers listening are sweating right now, we need to look at the business model enabling step three, because it completely upends how enterprise software is purchased.
It really does. It's fascinating. Usually, if you want a massive orchestration platform, you have to secure a massive upfront budget. You pay $1 million licensing fee, and then you spend 6 months implementing it, hoping it generates a return on investment. But the startups driving this autonomous optimization platforms like SystemsAutonomous, which are heavily featured in the engineering breakdowns, they have realized that traditional SaaS sales models create way too much friction for a concept that honestly scares traditional engineers.
Right. Pay us $1 million so our bot can kill your servers. It's a tough sell.
Exactly. So they have adopted an asymmetric business model based on performance contracts.
Walk me through the mechanics of a performance contract in this context.
The autonomous vendor comes to the enterprise and says, we will deploy our execution algorithms into your environment. We require 0 upfront capital.
0.
0. No licensing fees, no subscription costs. Instead, the platform monitors the environment, executes the right sizing autonomously, and tracks the exact delta in the cloud bill. They monetize strictly by taking a predefined percentage of the borrowed capital they successfully recapture.
Oh, that is brilliant. It perfectly aligns the incentives. The vendor is financially driven to find every single micro-optimization that can be safely executed because their revenue depends entirely on it.
And the buyer assumes 0 financial risk. If the system is too conservative and saves nothing, the enterprise pays nothing.
But if the system recaptures $10 million in idle compute, the vendor takes their cut, and the enterprise still walks away with millions in unexpected savings.
It shifts the optimization from a capital expenditure to a self-funding operational mechanism. But, as you alluded to, the financial model is only viable if the engineering team actually lets the vendor turn the system on.
Right. I can imagine the visceral reaction of a lid-site reliability engineer when a vendor says, we're going to let our algorithm autonomously terminate your live production servers to save some money.
They'd throw you out of the room.
The immediate response is, absolutely not. You are going to cause a catastrophic outage. So how do these autonomous systems guarantee that their pursuit of financial efficiency doesn't destroy production stability?
That fear brings us full circle. The terror of the autonomous bot breaking the system is the exact same fear that caused the engineer to over-provision the 100-pound suitcase in the first place.
It's a baseline fear.
Yes. The only way to overcome that fear is through verifiable mathematical safety. And that is why application-aware is not just a buzzword. It is the fundamental safety mechanism of autonomy.
Because the algorithm isn't flying blind. It's not looking at a blunt instrument like CPU and just guessing.
Exactly. Systems like SystemsAutonomous integrate directly into the application layer. They know what the application is experiencing down to the millisecond, and they operate on 3 non-negotiable safety mechanics.
Okay, let's hear them.
First, changes are strictly incremental. The algorithm will never look at an oversized cluster and instantly cut the compute capacity by 50%. It will shave off, say, 2%.
Just a tiny sliver. It degrades the capacity gradually to observe the impact.
Yes, and that brings us to the second mechanic. Continuous verification against service-level objectives, or SLOs. Before the system touches anything, the engineering team defines an absolute performance boundary.
Like a speed limit.
Like a speed limit. For example, this payment gateway API must respond in under 200 milliseconds 99.9% of the time. That is the SLO. So the autonomous system executes a 2% compute reduction, and then it watches the latency metric in real time.
It checks to see if the reduction pushed the application toward the boundary. What happens if the latency jumps to 250 milliseconds? The SLO is breached.
That triggers the third and most critical mechanic, sub-second algorithmic rollback. The system does not alert a human and wait for them to fix it.
Because that would take too long.
Way too long. The moment the P99 latency metric drifts outside the acceptable SLO boundary, the autonomous engine instantly issues an API command to restore the previous compute capacity. Because it operates programmatically, it corrects the compute deficit in milliseconds.
A human operator looking at a Datadog dashboard wouldn't even have time to register the anomaly before the system had already healed itself.
Exactly. It pushes the boundary of efficiency, but the moment it detects friction, it immediately retreats to safety. It's operating completely inside the reaction time of a human engineer.
And the proof points from the field deployments in the sources are incredibly compelling. SystemsAutonomous, for instance, has executed over 25 million autonomous scaling actions in live production environments with 0 reported availability incidents.
0 incidents. In the world of site reliability engineering, executing 25 million changes to production without a single Sev1 outage is almost mathematically unimaginable. It proves the model works.
We have concrete case studies here, too. No before, a major security awareness training platform, deployed this autonomous application-aware approach. They cut their AWS cost by 27% without touching their code, saving $1.2 million.
Incredible ROI.
And Palo Alto Networks, dealing with the massive erratic traffic spikes inherent in global cybersecurity, deployed autonomy and saved $3.5 million while maintaining strict, real-time responsiveness to threat data.
When you digest those case studies, you realize that this transition is about much more than just optimizing the FinOps spreadsheet. It brings the entire narrative back to that philosophical blueprint of restorative engineering.
Because the automation absorbs the risk.
Exactly. By deploying an autonomous system that works flawlessly, bounded by SLOs and instant rollbacks, the enterprise is taking the risk out of the hands of the human. The autonomous engine becomes the robotic arm handling the explosives on the assembly line.
It takes the pager anxiety, the absolute dread of a 3.0 a.m. alert because a node ran out of memory entirely off the shoulders of the engineering team.
The technology finally acts as a silent servant. The engineer doesn't have to spend 15 hours a week babysitting idle servers, cross-referencing billing tags, or arguing with finance about the size of a Kubernetes cluster.
They get to go home at the end of the shift, perfectly secure in the knowledge that the system is scaling itself safely, maintaining absolute stability, and maximizing capital efficiency simultaneously. It restores their dignity by removing the baseline of fear from their daily workflow.
It allows the engineer to return to the job they were actually hired to do, architecting new systems and solving complex logic problems rather than acting as a janitor for digital infrastructure.
It is a profound shift. Let's trace the arc of what we've unpacked today. We started by looking into that concrete room, visualizing the $27 billion bonfire of burned capital, driven by the very human instinct to over-provision for safety.
The 100-pound suitcase.
Right. We categorized the debris field, the idle non-prod environments running on weekends, the orphan storage volumes floating in the void, the zombie pipelines stuck in endless loops, and those oversized reservations that outlive their architecture.
We analyzed exactly why the traditional batch process manual audit is structurally incapable of catching continuous waste. The timeline just doesn't work.
And we saw why simplistic metrics, like CPU utilization, are dangerous traps that can take down critical systems, like the bank's ledger.
And finally, we mapped the solution. The transition to continuous application-aware detection using the golden signals of latency and traffic, ultimately culminating in fully autonomous execution.
Execution that scales infrastructure in real time, bound by strict service-level objectives to guarantee stability. It fundamentally rewrites how we manage scale.
It does.
But before we sign off, I want to leave you with a final, broader concept to consider. If you're listening, we focused heavily on how this benefits the enterprise buyer. But think about the downstream implications for the sellers. Right now, the business models of the massive hyperscalers, AWS, Google Cloud, Microsoft Azure, are heavily subsidized by that 40% fear tax.
They rely on enterprises over-purchasing capacity and leaving it idle. That's pure margin for them.
Exactly. So if autonomous optimization actually becomes the industry standard...
Oh, that's an interesting thought.
Right. If application-aware algorithms become perfectly efficient across the entire market, if every enterprise scales up and down to the exact millisecond and microwatt of compute actually required to serve their users with zero buffer and zero waste, does the concept of a massive, highly profitable, flat, monthly cloud bill disappear?
It would have to.
How will the giants of the internet have to adapt their fundamental economics when their customers finally figure out how to pay only for exactly what they use? It's a shift that could restructure the entire tech economy. Thank you for joining us on this deep dive. Keep looking for the hidden mechanics in the systems you interact with every day, and we will see you next time.